Okay, so in the last video, we went through different sets of steps that would let you find the probability of an event given a PDF. And here in this video, we'll do the same thing for finding CDFs and finding expected values. And so it's going to be kind of the same thing. There's more than one way to uh, do these things. And in different contexts, one way will make more sense, the other way might make less sense. It's also good to have multiple ways in order to check your work. Okay, so what we're about first is finding the CDF. Okay, so sometimes we have the CDF and we can use it to find probabilities. Sometimes we sort of implicitly find it when we're looking for a probability, but sometimes we care about it for our own sake. So that's what I'm kind of assuming here. This is what we want to know, the whole function for those cumulative probabilities here. And just to remind ourselves, what is the example we're looking at here? We're looking at a uniform random variable on the range 0, 2, writing weird things here. So for x between 0 and 2, the PDF is constant at 1/2 and it's 0 everywhere else. So we might see this written as x is distributed uniformly on the interval 0 to 2, and reminding ourselves just of yet another way to get this same information would be with a graph. There's 2, here's 1/2, where f of x is flat along the x-axis when x is less than 0 or x is greater than 2, but for the range where x is between 0 and 2, it's up here flat at 1/2. Okay. So this words, equations, picture, same way of getting the same information. Okay. For finding the CDF, I'm just going to sort of say there's basically two ways here. One, kind of continuing a point I was making previously, is you can look it up. So for something like this, a uniform random variable, we know that for a generic uniform random variable, something that's uniform on the interval C and D. So C and D are those parameters that are telling us which uniform random variable we're talking about, that we can look up in Wikipedia, we can look up in the notes for this class, we can look up in any book and find that the CDF, capital F, it tells us the CDF for a uniform random variable on the interval CD is 0 when we're looking at a probability that is less than the lower bound. It is 1 when we are looking at a probability that x is greater than the upper bound. And in between, when we're looking for a cumulative probability uh, that x is less than something that is in between the lower bound, it's supposed to be C there, getting ahead of myself, C and D. The cumulative probability is B minus C over D minus C. Let me fix one thing in the way I wrote the CDF here. I like to write my CDFs as a function of B so that I'm not finding myself saying things like the probability that X is less than X. That drives me crazy. So that I can say that the cumulative probability gives us the probability that X, the random variable, takes values less than B. That's why I'm using a different letter for the argument of the CDF. Okay, so if I went to the Wikipedia article on the uniform random variable, I should probably check, but I'm pretty sure that they would have the CDF written out like this. I am sure that my notes have it written out like this. And then the only remaining issue is to map our values for the particular uniform random variable that we're thinking about into the generic form. Okay, so our particular case here is one where C equals 0, that's my lower bound, and D equals 2. Okay, so my CDF for this particular case that we're interested in here is 0 for b less than 0. It is b over 2, that is b minus 0 over 2 minus 0 for b that is between 0 and 2. It's supposed to be a 0 there. And it is 1 for b that is greater than 2. So this is almost exactly what we did as a way of finding the probabilities in the previous lesson. And like, that's not surprising. Usually why people find the CDF is to find probabilities. And so what we're doing now is we're just taking something that was a step in the process of finding a probability and writing it down as its own function. And we might even, if we wanted to, graph it as its own function here. Okay, so we would have the CDF, so I'll do it in blue here, is 0 for b less than 0. So I've got my b here now on the x-axis. So it's 0. And for b greater than 2, it's up here at 1. So we've got these two constant levels here. And in between, it's this line with a slope of 1/2. Okay, so this graph is the cumulative distribution function for that particular random variable. Okay, and then once we have the cumulative distribution function, we can use this for any desired probability. Okay, we don't need to do the integrating every time. We don't even need to look it up every time. We just plug it in. All right. Yeah, so that was kind of a long-winded explanation of something that is really quite simple. Like, you look up the formula in a book, you get this, and you plug in your values of C and D to get that. I shouldn't belabor this to the point where I make a fairly simple thing seem hard. Let's see if I can avoid that with the second method here. Okay, so the second method, again, is to integrate the PDF. And this also is just going to look almost exactly like what we did before when we were looking for a specific probability. Now we're just looking for the formula that will give us any specific probability that we want. Okay, so we get the CDF by integrating the PDF. What that means is find the cumulative distribution function by integrating up to b the PDF with respect to x. Okay, so where am I getting this? I'm getting 0 as my lower bound here because below 0, the PDF is always 0 and the integral of that is 0. I just don't need to worry about that. I'm putting b as the upper bound here because that's like the definition of the CDF. The CDF is the area that is less than b here. So my b here is my b there. And now I'm just going to do the integration, and I'm going to keep that b in my definite integral. The b is going to be part of the formula for the cumulative probability. So that is just like it was before, x over 2 from 0 to b, and that is b over 2 minus 0 over 2 equals b over 2 for b less than or equal to 2. So essentially I've got the same thing. And to be honest, if I was trying to find a CDF for something that I didn't know and couldn't look up, I would need to have the equation, right? You have to have the equation to know, to integrate something, but I would try my best to draw the picture too, because the picture helps me with the tricky parts involving the cases here, that when X is in one range, it's this number, and otherwise it's in another. So the picture really helps me figure out those parts of the CDF. Okay, finding the expected value is almost the same, but there's one little difference. Okay. All right, so let's go to that. Finding. Again, you can look it up. For many of these random variables, you can look up a formula. Okay. So for the thing that we are thinking about, if X is uniform on CD, we found again in, I can't remember, I think it was lesson 7B, that the expected value for any uniform random variable, uniform on the interval C to D, the expected value is just the midpoint. Okay, it's C plus D over 2. So for our particular case where it's uniform on 0, 2, the expected value is 0 plus 2 over 2, it is 1. Nice. Okay. And that is a perfectly fine way to do it. If the random variable you're working with is something that you don't have a formula for, or you're just trying to wrap your brain around the whole idea of what we're doing with these CDFs here, the more first principles way to find the expected value is to integrate. Okay, and so yes, we are integrating the PDF with respect to X, but we've got the X in there. So what makes the expected value integral different from the CDF integral is this X. Okay, let's really belabor that. This gives a CDF, or it gives a cumulative probability. If you have an integral just of the PDF here, if you have the integral with the PDF multiplied by the variable, this gives you an expected value. Okay. Another less obvious, but still important difference between the CDF is for the CDF, we're integrating from 0 to B. And for the expected value, just like what we do with a discrete random variable, when we take the expected value, we're adding up all of the realizations, the possible realizations, times their probabilities. Here we're integrating the possible realizations multiplied by the PDF over all the possible values. So I'm writing from negative infinity to infinity here. It's not always negative infinity to infinity for uniform random variables. There's only a part of that range where there's any probability defined. Okay. So let's go ahead and do that integral and convince ourselves that what we got from the formula is the right answer here. Okay, so the integral of, so back to this point I was just making, that in the general formula, it's all possible ranges that the random variable could take. For our random variable that's just has positive probability over the range 0 to 2, this is the only range that matters for the expected value. So it's the integral from 0 to 2 of f of x times 1/2 dx. Okay. And so that is, it's the 1/2. And what is the function whose integral is x? Oh, I know, it's x squared over 2. Again, just sort of checking it in my head, taking the derivative of x squared over 2. It's 1/2, 2x, that is just x. So we get here x squared over 4 from, in both cases, dragging along my limits of integration here from 0 to 2. That is 2 squared over 4 minus 0 squared, square over 4. That is 4, so equals 1. And hooray, the formula is correct. What a relief. I'm being a little bit silly in saying that you want to check the formula. The formula for basic things like this in books, yeah, I'm pretty sure that that is a thing that is correct. You can believe the books. What I'm usually checking when I'm checking myself is how I'm using the formula. Am I putting the right values in for the parameters? That's, in one sense, not hard, but especially if you're going quickly or not quite understanding things, is a place where you could get confused. So the fact that these two things match let me know that the way I plugged in the particular parameters of this problem into the formula is correct. It's giving me the right answer. All right. One last possibility, as again, the normal distribution is always kind of its own little special thing. So what do we do with the normal distribution here? Well, in this case, the normal distribution is actually pretty nice. The expected value and the variance are the parameters, okay? Expected value mu and sigma squared. That's how we tell ourselves which normal random variable we're looking at. So the mu and the sigma squared parameters, mu and sigma squared, are like the C and the D for the uniform. Which normal random variable are we looking at? Okay, and we can just see those parameters right in the PDF. I mean, sometimes we might just be giving them words. That's quite a common thing with the normal random variable, but we can also just see them in the normal PDF. Okay, so the normal PDF, here it is, 1 over root 2 pi. I'm going to try to switch colors so you can really see where the parameters are. We have the sigma, the standard deviation, the square root of the variance down there, multiplying e raised to the power negative x minus, here's my other parameter mu, there's the expected value right up there, that whole thing squared divided by 2 sigma squared. Okay, so if you're looking for the expected value of x for normal, you could find it right up here, being subtracted from x and squared in the PDF. So if we saw something like f of x equals 2 pi, use a different color, times 3 e to the negative x minus 5 squared over 18. What that's telling us here is that the expected value is 5. It's right there in the PDF. And so ex equals 5. And the variance of x we got it 2 places where we should be able to check. So it is the square of what we have here, and it is 1/2 what we have there, and both of those things give us 9. And so we can just read those moments right off the normal PDF. Okay. So as I say, the point of this video and the previous one is to just kind of consolidate the steps that one goes through in working with continuous random variables on these basic questions. And I'm hoping that by kind of going over it in different ways, you're starting to see what the real steps that are the same in every problem are versus the little details that kind of vary from problem to problem.